Welcome to AI Paper Slop. We are jumping straight into a masterclass in scaling and systems engineering today. The paper is Motif 3, Technical Report by Motif Technologies, and here are the core insights you need right off the bat.
Let's hear.
A Motif 3 is a decoder-only mixture of experts language model. It has a massive 314 billion total parameters, but it only activates 13.2 billion parameters per token. It achieves this, massive capacity to compute ratio using a highly granular MOE layer with 384 routed experts.
Right, and it's selecting just 8 of those per token.
Exactly. And to make this actually run, it introduces Grouped Differential Latent Attention, or GDLA, to slash the KV cache memory while suppressing noise. And then for post-training, it uses this wild pipeline called multi-teacher on-policy distillation to merge 7 specialized teachers into one state-of-the-art agentic model.
Yeah, and I mean, for the technical practitioners listening to us right now, this paper is an absolute goldmine. We aren't just looking at, a list of final benchmark scores.
Right.
This is a deep, unvarnished look at the distributed systems engineering required to push a model of this scale over the finish line. We're talking custom MXFP8 kernels, dynamic context parallelism, and some incredibly elegant tweaks to the Muon optimizer just to keep the math stable over 12.5 trillion tokens.
So let's unpack the actual transformer blocks making this possible. We're looking at 53 layers, and 51 of those are sparse MOE layers.
Yeah, the sparsity here is hypergranular.
Right. 384 routed experts plus 1 shared expert using top 8 routing. So if I'm picturing this right, it's less like seeing a general practitioner for a cold and more like walking into a massive research hospital. You don't just see a general surgeon, you see a hyper-specific specialist for your exact rare condition.
Which is exactly how you get that incredible capacity without the compute penalty. Those 13.2 billion active parameters become incredibly potent per token because, well, they're perfectly tailored to this specific representation at that exact depths in the network.
Yeah, but the part that really requires some translation is the attention mechanism. Grouped Differential Latent Attention, GDLA.
Right, GDLA.
It's combining 2 massive recent breakthroughs, right? Differential transformer for noise cancellation and multi-head latent attention from DeepSeek for the KV state compression. But let's break down the why here. Why do we need differential attention in the first place?
Well, standard self-attention has a bad habit. It tends to allocate probability mass to completely irrelevant context.
Like background noise.
Exactly. It gets distracted by background noise in the prompt. So differential attention solves this by computing 2 separate attention distributions and subtracting one from the other. You are effectively isolating the common background noise and canceling it out, which forces the attention heads to focus strictly on the relevant signal.
But wait, calculating a noise cancellation path for every single attention head seems like it would waste a massive amount of compute.
It would.
Right, because in a traditional symmetric setup, you'd be wasting half your attention heads just modeling the noise you want to subtract. Doesn't that efficiency loss completely defeat the purpose?
It absolutely would, which is why GDLA uses an asymmetric group design. They don't split the heads 50-50. They partition the heads with a ratio they call G.
Okay.
In Motif 3, they use 64 signal heads and only 16 noise heads, so G equals 4.
So they dedicate the vast majority of the compute to actual signal modeling.
Right.
But how does the subtraction work if the numbers don't match?
They just repeat the output of each of those 16 noise heads across a group of 4 signal heads before doing the subtraction.
Oh, I see.
Yeah, you still get the noise-canceling benefits of differential attention, but it's heavily weighted toward the signal. And then they combine this with the compressed latent representation from DeepSeek's MLA to keep the KV cache tiny during inference.
Right, so both the signal and noise query paths share the exact same 16 kV heads using a single normalization and up projection for the compressed KV latent.
Exactly.
And to save even more compute, they use a hybrid attention schedule. So it's not full causal attention at every single layer.
No, that would be too heavy.
Right. They run 1 full causal layer, followed by 3 sliding window layers with a 128 token window, and they just repeat that pattern all the way down.
Which drastically reduces the overall FLOPs during pre-training and generation, while still allowing the model to aggregate global context at regular intervals.
Okay, so we have these hyper-specialists and a brilliantly compressed hybrid attention mechanism. That sounds great on paper.
Yeah, it does.
But managing activations across 53 layers with that much routing usually leads to exploding gradients. How did Motif physically tame the math to prevent the whole thing from blowing up?
They attack the stability problem at the foundational architectural level, starting with the residual connections.
Standard residuals being the problem, right?
Yes, standard residual additions where you just add the input of a layer to its output are notoriously problematic at scale. They cause activation outliers to accumulate and amplify as you get deeper into the network.
Got it.
So Motif 3 replaces standard residuals with modified manifold-constrained hyperconnections, or MHC.
Okay, so instead of one residual stream, they use 4 parallel streams. But the paper mentions these mappings are constrained to what's called the Birkhoff polytope,
Yes.
meaning they form a doubly stochastic matrix. So for me, and for the listeners trying to visualize this, does that just mean they are strictly bounding the energy of these activations so the math doesn't spiral out of control?
That is a perfect way to visualize it, yeah. A doubly stochastic matrix guarantees that the total information energy being distributed across those 4 streams sums to 1 across both the rows and the columns.
So you're preserving a convex mixing structure.
Exactly. Information gets routed, but it doesn't arbitrarily multiply. But Motif made one crucial modification to the original MHC design, which is the post-mapping multiplier.
The scale factor.
Yeah.
Originally it was set to 2.
Yeah, and the Motif found that a constant factor of 2 caused massive activation outliers at scale because of the repeated amplification. So they anneal that multiplier from 2 down to 1 over the course of pre-training.
Oh, wow, I see. So they get the fast early optimization behavior when the network is raw, but they physically squeeze out the persistent amplification before the math blows up later in training.
Exactly.
That makes perfect sense. They also ripped out the standard SWRGLU activation functions inside the MOE layers, right? They replaced it with expert-specific PolyNorm.
Yeah. In a standard MOE model, every single expert uses the exact same activation function.
Right.
But routing naturally sends entirely different token distributions to different experts. One expert might be handling syntax, another might be handling abstract math. Motif 3 gives each expert its own polynomial coefficients and bias, parameterized by a sigmoid to keep them bounded.
Okay.
This lets each expert adapt its nonlinear response to its specific data distribution.
It's like giving each of those hospital specialists their own custom set of tools, rather than forcing the brain surgeon and the dentist to use the exact same scalpel.
That's a great analogy. And we can see the mathematical proof that it works. When you look at the singular value spectrum of the expert date weights, expert-specific PolyNorm maintains a much higher effective rank than SWRGLU across the layers.
Yeah.
The learned gating transformations retain a broader set of active directions, meaning they don't collapse into a single dominant dimension.
Hold on. Speaking of collapsing, let's talk about the optimizer. They use the Muon optimizer, specifically parallel Muon, for the MOE layers.
Right.
But Muon is notorious for causing attention logits to explode. To stop it, Motif had to implement QK-clip to aggressively clip the logits every 10 steps. If Muon is literally blowing up the logits so badly that we have to step in and clip them manually, aren't we just shooting ourselves in the foot? Why use it at all?
I know, it seems contradictory on the surface.
Yeah.
But you use Muon because its ability to orthogonalize the momentum update using Newton-Schultz iterations makes the overall training efficiency undeniably better.
So the model converges faster.
Exactly. The real secret sauce isn't that they clip, it's how they clip. If you just scale down the query and key projections equally, you destroy the model.
Oh, because of the grouped query attention we talked about earlier.
Right. We have 64 signal heads and 16 noise heads sharing just 16 kV heads. If you clip the shared key projection equally, it receives gradient contributions from multiple query heads whose directions partially cancel each other out.
Ah.
So the key's effective recovery signal is much weaker than the queries. If you clip them equally, the shared key weights degenerate towards 0. They collapse.
To fix this, Motif designed an asymmetric splitting ratio for QK-clip. They shift the clipping burden heavily onto the query rows and barely touch the shared key rows.
Yes.
So it attenuates the overall logit and magnitude, but elegantly protects the shared keys.
It's a very subtle mathematical fix, but it saves the entire training run.
Incredible. So we have the math stabilized. But what does this actually look like on the hardware? Because running this distributed across massive clusters of B200 GPUs for 12.5 trillion tokens is an entirely different engineering nightmare.
O is a masterclass in distributed systems optimization, particularly how they handled fully sharded data parallel, or FSDP.
What did they change?
They implemented overlapping gradient reduced scatter. Normally, FSDP waits for a group to finish its backward pass before launching the reduction, which serializes the process and stalls the GPUs. They sit idle.
Right.
Motif modified FSDP to maintain a bounded window of in-flight reduced scatter operations, completely restoring the overlap between computation and communication.
And they leaned heavily into MXFP8 low precision for the MOE experts, right? But FSDP normally reshards parameters after the forward and backward passes. At this scale, gathering expert weights twice per microbatch would be a massive bottleneck.
A huge bottleneck. So Motif simply stopped doing it.
Just stopped.
Yeah. They keep the unsharded MXFP8 expert weights resident in memory between the forward and backward passes. Because MXFP8 is so compact, only 8 bits per parameter, these resident copies occupy memory that was already freed up by the backward pass.
Oh, wow. So it doesn't even increase the peak device memory.
Nope. They literally eliminated an entire all-gather operation per optimizer step.
They also pull a fascinating trick with activation recomputation to save memory, where they fold the routing weights into the permuted activation.
Yeah, that's a good one.
Normally, you apply the routing weight after the expert down projection, which means you have to keep the massively expanded expert output in memory just to compute the gradient. Motif folds the routing weight into the input permutation instead.
Exactly. The post-combine tensor is smaller than its inputs by a factor of the routing fanout.
Which saves a massive amount of memory.
And they desperately need that memory because they push the context length to 256K tokens. At that length, standard context parallelism algorithms break down. So Motif dynamically switches algorithms based on the layer type. Full causal attention layers use Ulysses, but the sliding window layers use window-aware ring attention.
This is such brilliant hardware awareness. Ulysses uses an all-to-all communication to transpose the sequence in head dimensions, so everyone gets the full sequence for a subset of heads. It's like a massive group broadcast where everyone shouts their piece at once.
Yeah, but for sliding window attention, where you only care about a local 128 token window, an all-to-all broadcast is massive overkill.
Definitely.
Window-aware ring attention only transfers the trailing W tokens from the preceding rank. It is a single halo exchange.
It's a localized bucket brigade instead of a global broadcast. Swapping strategies layer by layer based on the attention span is so smart.
Very smart.
But wait, there is a scheduling issue here. Motif packs multiple variable-length documents into a single 256K sequence to maximize throughput, and they mask the attention so documents don't attend to each other. Won't the GPUs that happen to get a batch packed with lots of short documents finish their attention math way faster than GPUs stuck with one massive, unmasked 256K document? Doesn't that create stragglers?
It absolutely creates stragglers. The quadratic nature of the full attention layers means a sequence with one long document requires exponentially more FLOPs than a sequence packed with 50 short documents.
Right.
If you naively dispatch these sequences, the fastest data parallel replicas finish early and just sit idle, waiting for the slowest one to finish. To solve this, Motif implemented an attention workload-aware rescheduling heuristic.
It's basically a massive game of distributed Tetris where every GPU independently looks at the falling blocks and agrees on exactly where they should go without having to text each other. How does that actually execute?
Every replica calculates an estimated computational cost for its packed sequences, based purely on the document boundaries. They all gather this cost estimate. Then, every replica independently runs the exact same deterministic longest processing time greedy heuristic.
Okay, so they sort the sequences by cost.
Right, and assign the heaviest sequences to the least loaded replica microbatch slots. Because the algorithm is deterministic, every replica arrives at the exact same global assignment without needing a central coordinator to broadcast the plan.
Wow.
Yeah. They execute a fixed-size all-to-all exchange to swap the sequences, and suddenly your massive workload variation is perfectly balanced across the cluster.
That is just beautiful engineering. So we've built this incredibly efficient hardware pipeline to pass tokens around perfectly, but all that infrastructure is useless if the experts themselves get lazy.
That's the MOE curse.
Right. How do you actually force 384 isolated experts to learn unique skills? Because MOE models have a psychological problem. The experts get overloaded, or they starve, or they just start copying each other.
This is the core MOE stabilization challenge. If a router initially favors a few experts by random chance, those experts get more tokens, they get stronger gradients, they become better at predicting, and the router favors them even more.
It's a positive feedback loop of doom.
It really is. Motif combats this early in training with decaying router noise. They inject Gaussian noise into the FP32 router logits. and decay it using a cosine schedule.
It's like forcing a patient to go see a random, out-of-network doctor just for exploration. But doesn't adding noise to the router intentionally degrade the loss early on? Why would you sabotage your own model's routing?
You'd think it sabotages it, but the data shows the opposite. The early noise forces exploration before the experts can prematurely lock into a suboptimal distribution.
Oh, I see.
It actually accelerates the formation of balanced loads. The maximum tokens per expert falls toward the median load much earlier in the run, and the loss drops faster in the long run because you are effectively utilizing your whole parameter budget rather than letting half your experts starve.
They also use an FFN magnitude regularization to stop the feed-forward networks from blowing up. But instead of hard clamping the activations like standard models do, they use a soft auxiliary penalty.
Yeah, a mean squared rail U penalty applied only to values above a certain threshold.
Why not just hard clamp?
Hard clamping is dangerous because it discards magnitude information and completely kills the gradient once you cross the threshold. By using a soft penalty, normal activations are untouched. But if a channel spikes, it gets penalized while still maintaining a non-zero recovery gradient.
It discourages those super weight-like outliers without breaking back propagation.
Exactly.
And while all this is happening, they are constantly running expert health monitoring in the background. They track the minimum to median dispatch ratio to see if an expert is starving.
Yes, that's standard.
But what I found fascinating is that they monitor the maximum cosine similarity of the output activations, not the weights. Why look at the activations?
Because looking at the flattened high-dimensional weight matrices of the experts is mostly uninformative. You are looking for functional collapse. The scenario where two experts are nominally getting different tokens, but they are outputting the exact same representation.
So they're redundant.
Right. By computing the cosine similarity of the average output vectors over the routed tokens, you can directly see if experts have become redundant. If that similarity spikes above 0.8, you have severe functional redundancy, even if the routing load itself looks perfectly balanced.
It's all about making sure the experts are actually learning distinct concepts, which brings us perfectly to the final act of this paper.
The post-training.
Yes. Once pre-training is done, the model is smart, but it's raw. The post-training pipeline here is basically an AI university, and it is arguably the most fascinating part of the whole architecture.
It represents a total paradigm shift. They don't just fine-tune a single model. They start with a general supervised fine-tuning base, or SFT.
Right.
They use a multi-token prediction head with assistant-only loss masking, and they specifically target failure-prone decisions in agentic trajectories. But that's just the baseline.
From that SFT base, they branch the model into 7 separate specialist teachers. 6 of them are trained using reinforcement learning via GRPO, and 1 software engineering teacher is trained via SFT. So they have teachers for agentic tool use, professional work, long context, math, code and science, and chat.
And you have to look closely at the specific reward designs they use for these RL teachers. For example, the chat teacher uses a piecewise constant shaping function based on token length.
Wait, why single out token length for the chat teacher?
Because if you don't, reinforcement learning policies figure out a cheat code. They realize human preference models love long, detailed answers, so they just generate massive walls of text to gain the reward.
Of course they do.
Yeah, the piecewise function acts as a hard ceiling to slap that behavior down and penalize overly long answers.
Okay, so you have these 7 incredibly smart specialists. Then comes multi-teacher on policy distillation, or MOPD. They take the 7 teachers and consolidate them back into a single student model.
Right.
It's like cloning a student, sending the 7 clones off to get 7 different PhDs in completely different fields, and then mind-melding them back into a single super genius.
Pretty much. They generate on-policy trajectories with the student, route each example to the appropriate domain specialist, and then distill the scalar log probability assigned to that token by the teacher.
But here's my biggest question with MOPD. If you optimize these teachers entirely separately, using RL in different environments, don't they suffer from catastrophic forgetting?
That is the risk.
Don't they forget their general knowledge or actively fight each other during the distillation phase when you try to cram them all back into one brain?
That is the core risk, yeah. To prevent the teachers from overriding the student's general knowledge, Motif uses a technique called the ICE-PIOP filter.
Let's break down this ICE-PIOP filter. How does it actually work?
It looks at the importance weight of every single token being generated. That's the ratio between the student's current policy and the generation policy. Motif set a strict bound, 0.2 to 5.0.
And if it's outside that?
If the import sway falls outside that window, they just drop the token from the distillation loss entirely.
Wait, so if a teacher has drifted too far into the weeds of its specialty and it's suggesting a log probability that is radically different from what the base student would do, the filter just ignores the teacher.
It completely ignores it.
Yeah.
And they take it a step further. There are absolutely no environment rewards included in this distillation phase.
Strictly token-level distillation.
Exactly, just the log probabilities. Furthermore, they keep the multi-token prediction parameters and the MOVI routing parameters completely frozen during distillation.
So the routing configuration learned during general SFT stays locked in?
Right, anchoring the model's general capabilities while the internal weights absorb the specialized knowledge.
So what does this all mean when you put it to the test? The benchmarking results are staggering. Motif 3 absolutely dominates in agentic and tool use tasks.
It really does.
It scored 35.3 on the Tau 3 banking benchmark,
Yeah.
topping the list. It hit 51.5 on IT Bench A for Kubernetes incident diagnosis, and it scored a 76.2 on SWE Bench, verified for software engineering.
It completely validates the entire pipeline. The model maintains broad, general reasoning capabilities while exhibiting elite performance in long-horizon multi-step execution. It proves that combining hypergranular sparsity with stable, large-scale RL distillation actually works at the frontier.
It really does. And, it leaves you with something profound to ponder. Motif 3 proves that scaling in AI isn't just about throwing more compute at making a single model wider or deeper.
No, it's not.
It's about turning the training pipeline itself into a multi-agent system. You have specialists explicitly teaching a generalist. It makes you wonder what happens when we take humans out of the loop entirely.
That's a wild thought.
Right. What happens when these specialized teacher models start designing their own custom reward functions and generating their own synthetic curriculum to push the student model past the limits of human knowledge?
That is the frontier we are rapidly approaching.
Thanks for joining us for this deep dive into Motif 3. See you next time on AI Paperslop.